All right, let's just jump right into this explainer and tackle what is absolutely one of the biggest mysteries in fundamental physics, the reality of time itself. It's something every single one of us experiences, right? Every second of every day. We feel the past fading, the present happening, and the future arriving. But what if I told you that in the absolute most fundamental equations describing our quantum universe, time doesn't actually exist? It's kind of wild to think about. Today, we're going to explore a groundbreaking new study that uses a tabletop laboratory experiment with ultracold atoms to literally create a mini-universe. And the whole point? To figure out where time actually comes from.
So let's kick things off with Section 1, the missing time mystery. To really grasp this paradox, we first have to look at the foundations of quantum gravity. We're talking about that messy intersection between the incredibly large and the unimaginably small. We all experience time flowing. But if you look at the math governing the entire universe, time completely vanishes from the equation. Seriously, it's just gone. While Newtonian mechanics, standard quantum mechanics, and even relativity all allow us to describe how things move, they actually offer no built-in temporal orientation. If you run the math forward or backward, it looks exactly the same. There's simply no fundamental arrow pointing from the past to the future. Enter the Wheeler-DeWitt equation. You can think of this as a cosmic crime scene where our concept of time is just nowhere to be found. It describes a universe in this pure static state. There's no parameter for t, no external ticking clock to sequence physical changes. So the big question is, how on earth do we get the flow of time we experience in the real world out of a static, completely timeless equation?
That brings us to Section 2, entropy, the cosmic clock.
Well, to solve this missing time mystery, we need a solid clue. And we find it right here in the only fundamental asymmetry in physics. While all those other frameworks work perfectly fine backwards or forwards, entropy, our arrow of time, only pushes toward more disorder. The second law of thermodynamics tells us that coarse-grained entropy must increase. It's literally the only physical law that demands a strict direction, an irreversible flow. It is the exact reason a shattered glass doesn't spontaneously reassemble itself on your kitchen floor. But how does this actually translate into a clock for the universe? This builds into a really fascinating concept called relational time. In relational time approaches, there is no master clock sitting outside the universe. Instead, the universe effectively checks its own watch by measuring entropy moving between different parts of itself. Imagine just partitioning the universe into two chunks, an observed subsystem and an unobserved subsystem. One part acts as an entropy source or sink for the other. As entropy flows between these two sectors, it creates a local tick. Time isn't some external master clock. It's an emergent relational parameter. It's simply the act of one piece of the universe changing in relation to another.
Which leads us right into Section 3, building a mini-universe. Now, instead of just getting bogged down in abstract cosmology and theoretical math, an incredible team of scientists decided to actually test this by building a tangible, tabletop laboratory analog. And what you're seeing here brilliantly illustrates that mini-universe. These are experimental absorption images. The researchers used optical dipole potentials, essentially strategically intersecting lasers, to create a conservative harmonic trap. Notice how they partition this trap right down the middle with a thin optical barrier. That divides it into an observed bright sector on top and an unobserved dark sector on the bottom. When atoms cross that barrier and populate the bright sector, that's marked by those blue stars, an analog Big Bang. And when the bright sector contracts and collapses back into the dark sector, marked by the green stars, well, that's an analog Big Crunch. So how exactly does this mini-universe work? By isolating the system completely from any external dissipation, the researchers simulated an effectively closed many-body system, a true mini-universe. They started by creating a Bose-Einstein condensate in a trap. Then they projected a remarkably thin 8-micrometer optical barrier across the center using a digital micromirror device. Depending on how high they made that laser barrier, atoms, and therefore entropy, would bleed over into the observed bright sector. And because the whole thing is perfectly isolated on the experimental timescale of about 100 milliseconds, they could track exactly how this closed universe behaves without any messy outside interference. And to really ground this in reality for a second, this entire mini-universe is composed of roughly 24,000 rubidium-87 atoms. By keeping the number of atoms so highly controlled, they created this pristine, perfect environment to test massive cosmic quantum gravity ideas right on a tabletop scale.
It's honestly amazing that we can use just 24,000 cold atoms to probe the fundamental nature of existence.
All right, let's get to the results in Section 4, reading the entropic clock. So we've got our mini-universe, and we have atoms flowing back and forth. But how do we actually read the clock in a universe made of 24,000 cold atoms without, cheating and just using the clock on the lab wall? Notice the contrast here between the traditional way physicists might measure this versus this new entropic time. Traditionally, scientists might use a physical variable like a massive scalar field, which here just corresponds to the center of mass of the atoms. But there's a huge flaw with that. In a universe that expands and then recollapses in a big crunch, that physical variable actually reverses direction. It's ambiguous. It fails to span from the Big Bang to the Big Crunch monotonically. But entropic time? The researchers constructed this mathematically purely from the flow of entropy into the bright sector, and it successfully ticks forward continuously. It increases monotonically, meaning it never goes backward. It perfectly mimics a real-world experience of time. Take a look at this graph. It's a direct visualization of time literally being created by entropy. The researchers evaluated this entropic internal time from their experimental data and plotted it against standard external lab time. The different colors you see represent different heights of that laser barrier. Notice how the entropic time actually flows faster. The slope is much steeper when entropy transfers efficiently between the dark and bright sectors. And look at those red triangles right at the bottom. When they raised the barrier so high that no atoms or entropy could cross at all, the system reached a stationary state. It was an analog heat death, and the internal entropic time entirely stopped ticking. Absolutely no entropy flow means absolutely no time. So they proved they could read the clock, but could they use it to do actual physics? By comparing the real-world lab measurements on the left with the stunning numerical simulations on the right, we see the absolute triumph of this experiment. The researchers successfully wrote an entirely new Schrödinger equation, but instead of being parameterized by regular time, it was parameterized solely by this newly defined internal entropic clock. And as you can see, this new equation acts as an entropy-dependent energy pump. It completely and accurately predicts the cyclic big bangs and big crunches of this mini-universe. The simulation perfectly matches the physical reality of the atoms. Let's wrap things up with Section 5, the future of time. Look, this isn't just a neat laboratory trick with some lasers and rubidium atoms. It represents a major, game-changing leap in how we investigate the fundamental fabric of reality. What you should really take away from this explainer is that we now have experimental proof that time can act as an emergent, relational property driven entirely by entropy. We can take the most abstract, untestable mysteries of canonical quantum gravity and actually probe them on a tabletop. Moving forward, scientists can use these cold atom platforms to test mind-bending concepts like Willenkin-type tunneling, where entire universes might just spontaneously tunnel into existence, or investigate whether the universe experiences a true singularity or a quantum bounce during a big crunch. It finally provides a measurable arrow of time based purely on the thermodynamic flow of entropy between subsystems. I want to leave you with a rather profound thought to chew on, because this completely changes how we might perceive every single passing second of our lives. If time at the cosmological scale is really just a relational illusion created by entropy shifting from one unobserved sector to an observed one, is our own daily experience of time simply the universe checking its internal entropic watch? Next time you look at the clock on your wall, just remember, the true clock of the cosmos might just be the inescapable flow of disorder. Thank you so much for joining me on this explainer, and as always, keep questioning reality.